Hi, welcome to a new video. Today we want to look at how datasets affect plate notation or how plate notation can be used to express datasets. This video will contain a lot of coding and TensorFlow probability and is probably a nice follow-up video on my original introduction to plate notation. Okay, let us start with the following graphical model. So we have a weather random variable and a happiness random variable, and the weather is affecting your happiness. We call the weather shorthand W and the happiness shorthand H. The weather can either be bad or good, same for the happiness, and we encode this as 0 or 1. And recall you have a discrete random variable, two states. This is a Bernoulli distribution, and the Bernoulli takes one parameter. This is the theta, the probability of the event being 1. And so we have to save the probability of the weather being good. And since the happiness is taking two parameters, it can be like it's happiness of being happy when the weather is bad and being happy when the weather is good. So we have to save kind of an array of thetas. And we can also denote this by deterministic variables, by these square brackets. So we have a theta W and we have a theta H vector that go into our graphical model. And by the rules of directed graphical models, we can factorize the joint. The joint is P of W and H and is given as P of W times P of H given W. Okay, now we have this dataset or this model, and you would now observe your daily life, for instance, and you observe the weather and the happiness for a couple of days. So now observe for, and let's say n days, and then you get a dataset, and this dataset contains tuples with the weather and happiness observation. So for instance, say, yeah, we have good weather and we are happy, another day of good weather and happiness, a day of bad weather and happiness, and so on, or maybe even other combinations, whatever you observe. And if you now want to calculate the likelihood, so we want to calculate the likelihood, what you would do is, well, you know these are n observations of your model. You just take the product over the probability of an instance of the sample that you get, of all the samples. So P of D, or the probability of the dataset, is the product from 0 to n minus 1 over the probability of the weather being your ith observation and the happiness being your ith observation. So for instance, P of 1, 1 times P of 1, 1 times P of 0, 1, and so on and so forth. Okay, now assume someone would come up to you and propose a different way of doing this. And he says the following. Imagine I have some random variables, a bunch of random variables, and I have a 0 weather node, and I have a 0 of happiness node, and I have an n-1th weather node, and I have an n-1th happiness node. The 0th weather node is affecting the 0th happiness node, and the n-1th weather node is affecting the n-1th happiness node. So there are our n nodes here, or 2 times n nodes. And then, of course, you know, if he says something like this, and he probably also proposes to you that he uses a plate notation, so we can express this. This is equivalent to the following, where we have the weather random variable and the happiness random variable. So weather I, happiness I, and ith weather node is affecting the ith happiness node. Not the 0 is not affecting something else here. And then he has to put a plate around here in order to say, well, this is repeated n times. And then he also puts in the deterministic nodes. They are not repeated since he keeps the same probabilities. So this is a theta weather and this is a theta happiness. And now he has some sort of what we call a random vector. So he has a W vector, and I call this with an underscore in order to say this is a vector. And this consists of the following. So we have a W0, we have a W1, all the way to a Wn minus 1 transpose, because it's a vector in this sense. And you can think of this as like a random vector, or in essence, these are n independent Bernoullis. And what he does, he essentially encodes the same with his model as you would do if you observe your weather for n times. However, some kind of the idea of observing the weather n times is hard-coded into his model. So hard-coded with n observations. This would also mean that if he is observing his model, an observation of his model would mean that he is like observing it 10 or like n days at once. So an dataset, or let's say an observation of this model would contain all n days. But essentially, if he is trying to calculate the likelihood with his model, this would yield the same likelihood. It's just two ways to express it. And we can now look into TensorFlow probability in order to see how it is expressed there. Okay, let's look at TensorFlow probability. For this, I will open up an interactive Python session. Then we import a package in order to suppress TensorFlow warnings. Then we need TensorFlow itself. And we need TensorFlow probability as TFP. Okay, before we start creating our model, let's just fix the theta values, because they are not relevant for the further discussion. So we just fix them to an arbitrary value. Assume we know them, because there's nothing we want to infer right now. Okay, so the theta weather will be a constant value, and we say, for instance, it's 80%. So 80% chance of good weather. Then the thetas for the happiness will be again a constant, but we need two values, of course. First, the chance of being happy at bad weather. Let's say it is 70%, and the chance of being happy at bad weather, and let's say it's 95%. Okay, then let's create the first model, and this was the model where we did not have a plate notation, so we call this the model 1. And the model 1 is taking two parameters. It is taking a probability for the weather, and it is taking weather to happiness probabilities. And the first we have to do is we have to sample a weather, or like create the weather random variable, and it is a random variable, so we yield it. And it's not just any random variable, it's a root node, so we have to define it like this. And we use the distribution, it's a Bernoulli, and it has a probability of the weather prop. And we call it the weather. Oopsie. Let's fix this. Okay. And then we're fine, good to go. Then we can define the happiness, which is another random variable, so we yield again. And then we have a Bernoulli because it's no root. And the probability here is the weather to happiness array accessed at the weather. Recall, weather is encoded either as 0 or 1. So this will then return either the 0th or the first element. And the name here is the happiness. Oh, here we go. Okay. That's it. And then we can instantiate our model. So we call this joint 1, for instance. And we need tfp.distributions.joint_distribution coroutine auto-batched again. And we have a generator, but our generator is taking arguments. So we have to bind this generator. We use a lambda for this, and we say it's model1, and then we have to bind it with our fixed theta values, theta weather and theta happiness, and that's it. Then we can look at it and see it's a joint distribution with a weather and a happiness, and we can sample it once and get good weather and happiness, and we can sample it 10 times, and then we get, for instance, bad weather but happy, and so on and so forth. Recall, this is actually the way that the other person was proposing his data set, so that he has two arrays instead of tuples. But this is just caused by the way that TensorFlow probability works under the hood. You have to read it like a tuple with 0 and 1, 1 and 1, and so on. Okay, now let's look at the second model. But before we go there, let us just quickly save this as a data set. So we have 10 samples, and we call this our data set. And we can look at it again. Now, of course, it has also different entries. And if we calculate our likelihood of the data set, then we produce our joint distribution, the probability command, feed in the data set, and then we know, well, we get a bunch of numbers, and we have to reduce them in order to get one value. So we reduce the product. And this is the likelihood of the model with the first description of the model, or the first description of our modeling procedure. Okay, let's now define the second model. And for this, we need another generator, model 2. And this time, it's not just only taking the weather probability and the weather to happiness probabilities, but it's also taking another argument, and this one is the number of days. The first random variable will be somehow similar, but still a little different. So we have the weather, and we yield it because it's a random variable. And we have a distribution, and again, it's our root. And it's still a Bernoulli. And now this is the point where TensorFlow magic comes in, or TensorFlow probability magic comes in. So we still have to define its probability, but we are defining it by the help of an array. So we have the weather probability, and we multiply this with an array or a tensor with only ones in it, and this tensor is of size n days. So actually we are providing the Bernoulli with an argument that is a tensor of 10, for instance, 10 days with a certain probability of the weather. So it's 10 times the same. And this is what I meant by a vector of Bernoullis, or a vector of independent Bernoullis. These Bernoullis are independent of each other. Okay, let's close this down. Yep, that should be it. Oh, this was incorrect. So we have to now add, of course, our happiness, and we yield this, and this is a distribution Bernoulli and probability. And now we have to define its probability. So if we would do it similarly as we did it in model 1, where we just take this argument and then take it at this index position, we would get an error, because weather is not just a scalar now, but it is a tensor. So we can't just access another tensor with a tensor. So we need some sort of a command here, and the command is called tf.where. And we will check on the vector of Bernoulli drawings and say we check where the weather is 1, or where the weather is good, and where it is good, then take, if this is true, then take the weather to happiness 1, so take it at the good weather, and if it is not the case, then take it for the bad weather. We will close it down, and then we have our second model, and we can instantiate it, join to tfp.distributions.joint distribution coroutine autobatch. and we have to bind the generator again. So we will use model to feed it with our theta weather, then with the theta happiness. And lastly, we say that we want 10. And here, see again, this is hard-coded into our model. And that was the big difference from these two models, actually. Okay, and then we have a joint 2. You can look at it. It's an joint distribution coroutine auto-batched, but we forgot to give them names, but there should be weather and happiness here. But we now see that the shape of those distribution is 10 by 10. So it has 10 samples for the first and 10 samples for the second, which also means if we sample it once, so if we sample it once, but we get 10 samples. So essentially we're getting the same as if we would sample it 10 times, if we would sample our first model 10 times. And if we now sample this one 10 times, what we actually get is we get 10 times 10 observations. And the cool thing now is, if you recall that earlier we used TF reduce prop in order to access the likelihood of the first model, and we got this value. We can now use our new model, our joint 2, to do the same thing of our old data set, and we see we get the same value, but we don't have to reduce it because the size of the data set was hard-coded into our model, which also means that our model wouldn't work if we would feed it less entries, for instance. So if we would just feed it the first 8, or this probably won't work, but if we, let's say, for instance, feed it a tuple of good weather, good weather, good weather, and good mood, bad mood, then it would say incompatible shapes. Whereas for our joint 1, this would be a legit call, and we would get 3 values out here. Okay, now we have seen how to implement this in TensorFlow probability, and you now see the 2 ways, but you now might ask yourself, what of the 2 ways is the correct way of doing it? Because, I mean, they kind of led us to the same result. The one was a little easier to use, but maybe it has a hard-coded n. Maybe let me show you a scenario where you would have to use the second approach. Okay, for this I will keep our model. So we have weather, you have a happiness, and I've weather, and we have an I've happiness, and there is a plate telling us we have n of these observations, and then the weather is affecting the happiness, and we keep the deterministic node for h, which is a theta h array. But contrary to before, this should be deterministic, so we have to put this in a square. But contrary to before, we now make the theta for the weather a random variable, and we keep it observed for simplicity. And we say it's theta weather, and this theta, so the probability of good weather, is now affecting our weather. But this theta is valid for all the n samples that we take. And usually if you would do something like this, then the theta is a prior to your probability, and the easiest way to model this is with a beta distribution. So you say the theta weather is distributed according to a beta with an alpha and a beta parameter. So this node is taking 2 deterministic parameters, an alpha and a beta. And you can think of this as following. You would be observing the weather and your happiness throughout the year. So you would be observing it for 365 days. And you would select a theta for 1 year. So the theta is distributed between 0 and 1. So you would choose one of these 2 probabilities. And then you would observe your weather and happiness over a year. So this would be the observation. Let's say this for instance. for 1 year. So n would be 365 days. Okay, let's implement this new model in TensorFlow probability. So we will create a new generator. Let's call this model 3. And it takes an alpha, so the hyperparameters, alpha and beta for the beta distribution. Then it takes the weather to happiness props, as they are still deterministic. And it takes the number of days. And our new root node is the theta. So the theta, let's call it just theta, and it is root node, so root, and then we need a beta distribution, and the beta takes the alpha and the beta parameter, and the name is theta weather. Then we can, oh, surely we have to yield it because it's a random variable. Don't forget about this. So the weather is then another yield, another random variable. And we do tfp.distributions.Bernoulli. Note it's no longer a root node. And it is taking the probability argument. And here we know the theta is the probability we get out. And we now have to multiply it with the ones array. So it is theta times tf.ones of n days. So n days, one array in a sense. And then lastly, we have the happiness random variable, which is a yield. And we take a Bernoulli again. And of course, we should also give it a name. Shouldn't forget about this once again. So name is weather. And here, for the probability, we do our where switch again. So we check where the weather is 1, and at these places where it is 1, we take the 1th index or the 1th element of our theta arrays. And if it is 0, then we take the 0th element. And then we give it a name, and this is the happiness. Close it down, and then we can create a joint 3, and this is distributions, joint, distribution, coroutine, auto-batched. Okay, well, we have to bind it, so I forgot to define the parameters. Let's do this first. So we have to define an alpha, and this is a constant value, it is a scalar value, and let's, for instance, say it's 10.0, and a beta is, for instance, 5.0, and in case you're not familiar with beta distributions, this is a distribution which has like a peak slightly shifted to the right, so theta values from 0.5 to 1.0 are more likely than theta values from 0.0 to 0.5. Yeah, so from 0.5 to 1.0 are more likely. Okay, and then let's create the joint, and we need the joint distribution coroutine auto-batched, and we have to bind our generator again. So we do model 3, and we feed it alpha, beta, and we feed it the thetas for the happiness. And then, I mean, you should probably, like according to what I said earlier, put in 365, but for brevity we use 10. And let's put this down. Then let's look at the object that we got out, and joint distribution, create. So we have a theta weather, which is a scalar, and we have weather and happiness, which are both of type shape 10. And if we sample this once, then we get, okay, we are in a year where good weather appears with 62%, and then we observed 10 days with this weather, and this affected our happiness in this way. And we can sample it again, and it will be something like this. And if we sample it 2 times, for instance, that's getting really interesting now. Okay, and here we see that we then have an array of probabilities for the weather, and then we have 2 times 10 days of weather and 2 times 10 days of happiness. Okay, in the last example in TensorFlow probability, we saw that if we take 2 samples, then we are getting some kind of composite data set. So we are then, for instance, observing 2 years. Let us look how this would be noted down in plate notation. So then let's say observing for multiple years. And for this, I will be copying most parts of this of the model that we created here. So let me copy it. And let's bring this down, like this. And now if we would model it for more than 1 year, we would then incorporate more plates into it. So I will, for this, remove what we have here and put this a little bit further down and call this was the beta. And then we have another plate which then sits like this, incorporating these variables, and it would be giving us the number of years. Let's call this M. And so we would have a second index. Let's call this J. And the J index is running from 0 to M-1. And now also note that here it might look we have 2 indices, but the W is just an indicator. That's the theta for the weather, but it's the theta for the weather in the jth year. And now you would have M years, and so on and so forth. And you can use this in any kind of combination that you want to create a model with plate notation. And TensorFlow probability also offers the flexibility to create efficient models with the help of these plate notations. And this brings me almost to the end of this video, and I would like to give you some leaving notes. Why we did this is I wanted to emphasize that plate notations are related to length of datasets, or plates can be used to represent samples. And it's not entirely clear when you will be using a plate or when you will be sampling your dataset multiple times, and it's like implicitly a plate. But it's really important to keep this in mind, that this is used in different environments and for different applications. And this one comes especially handy when what we also see here with the years. And so let's call this especially useful or especially needed in composited or composed plate notation. So if you have nested plate notations. And probably the more examples you will see with this, the more clearer it will get. But anyways, I hope you learned something today, and thank you for watching. And here you will see more videos that might help you during your learning journey. Thank you.